Somewhere over Italy, a stopwatch is running backward. Not metaphorically. A beam fired from one lab arrives at another 730 kilometers away, and the clock says it got there before it should have been physically possible. In the control room, someone is staring at a number on a screen that keeps refusing to change no matter how many times they rerun the math. 60 nanoseconds. That's the gap. That's the whole crisis, sitting inside a sliver of time too small to blink through. A physicist checks the timestamp a third time, half expecting the software to correct itself. It doesn't. If this number is real, something has just outrun light itself, and the entire framework holding up modern physics needs to be torn open and rebuilt. But none of that explains how they got here, or why this particular lab, on this particular night, ended up staring into a result nobody wanted to be true. 9 months earlier, none of this was supposed to be possible. For most of the 20th century, the speed of light wasn't just fast, it was final. 299,792,458 meters per second, taught in classrooms as the one number the universe refuses to negotiate on, printed in textbooks like a fence around what's allowed to happen. Physics students learn it the way they learn gravity. You don't argue with it, you build around it. Spaceships in science fiction strain against it. GPS satellites correct for it. Particle accelerators spend billions of dollars respecting it as an unbreakable ceiling. For over a century, every experiment designed to catch light speed slipping just confirmed it further. Physicists had measured it, remeasured it, and built entire careers on the assumption that this ceiling would hold forever. It felt less like a scientific finding and more like bedrock. And in a lab tucked into the mountains outside Rome, a detector kept doing exactly what it was built to do: watching, counting, recording. One quiet anomaly in a lab dataset was about to become impossible to ignore. The person who made light speed sacred wasn't chasing headlines. In 1905, a 26-year-old patent clerk named Albert Einstein was wrestling with a problem buried inside Maxwell's equations, the mathematical rules that describe how light and electromagnetism behave. Those equations kept spitting out the same strange answer: light should move at one fixed speed, no matter who's watching or how fast they're moving. That broke every intuition physicists had about motion, where speeds are supposed to add and subtract depending on your point of view. Einstein made a choice that changed everything. Instead of assuming the equations were wrong, he assumed they were right and rebuilt the rules of space and time around them. If light speed had to stay constant, then time itself would have to bend to make room for it. That single postulate became the foundation of special relativity, and it held up flawlessly for over 100 years. But a postulate is still just an assumption dressed up in a century of good behavior. That assumption was about to be tested in a way nobody expected. Relativity isn't just theory sitting in a textbook. It runs underneath your phone right now. GPS satellites orbit at about 14,000 kilometers per hour, and their onboard clocks tick faster than clocks on the ground because they're farther from Earth's gravity. Left uncorrected, that mismatch would throw your location off by about 10 kilometers a day. Engineers had to bake Einstein's equations directly into the satellite firmware just to keep your map app pointing at the right street. At CERN, physicists slam protons together at 99.9999991% of light speed, and every collision plays out exactly the way relativity predicts, down to fractions of a percent. For 100 years, in labs and in orbit, the universe kept following the same rulebook. Then a strange result started showing up where it shouldn't. In 2011, a detector called Opera sat buried under a mountain in Gran Sasso, Italy, 730 kilometers from CERN's particle accelerator in Switzerland. Its job was simple: catch neutrinos fired straight through solid rock from Geneva and measure how long the trip took. Neutrinos barely interact with anything, so they punch through the Earth's crust like it isn't there, arriving in about 2.4 milliseconds if they're moving at light speed. The opera team had spent 3 years refining this measurement, syncing atomic clocks at both ends with GPS down to the nanosecond and pinning the distance to within 20 centimeters mines. This was not a rushed calculation. It was one of the most carefully calibrated timing experiments in the world. And when they finally ran the numbers on thousands of neutrino events, the result made no sense at all. 60 nanoseconds. That tiny number was about to shake physics to its core. 60 nanoseconds is a sliver of time, so small a hummingbird's wing beat looks glacial by comparison. But over a 730 kilometers run, arriving 60 nanoseconds early meant only one thing: the neutrinos had covered that distance faster than light possibly could. Not by a wild margin, just a hair, about 0.002% over the limit. Small enough to sound like a rounding error, and large enough to break a law that had never bent in over 100 years of testing. If light is supposed to be the fastest anything can travel, then something outrunning it doesn't just tweak the numbers. It threatens the order events are allowed to happen in. Cause is supposed to come before effect, everywhere, for everyone watching. A confirmed faster-than-light signal could scramble that sequence entirely, opening the door to effects arriving before their causes. The opera physicists checked their data obsessively, ran it back through their statistics, and the anomaly refused to go away. Every recalculation, every cross-check, kept landing on the same impossible number. The team had two choices: bury the result or stake their reputations on it. On September 23, 2011, the opera team held a press conference at CERN. They stood in front of cameras and said it plainly. Neutrinos had traveled 730 kilometers from Switzerland to Italy in 60.7 nanoseconds less time than light would need. The measurement had a confidence level of 6 sigma, meaning the odds of this being random noise were about 1 in 500 million. Physics forums lit up within minutes. News outlets ran headlines about Einstein being wrong. The paper went live on Archive that afternoon, co-signed by 160 researchers who'd spent months checking the math. But the opera scientists didn't declare victory. Lead spokesman Antonio Ereditato told reporters they were releasing the data specifically because they couldn't find the error themselves. They were asking the world for help. Not everyone believed them, not even close. Nobel laureate Sheldon Glashow calculated that if neutrinos really moved faster than light, they'd radiate away energy and arrive at the detector with far less power than opera measured. They didn't. Other physicists pointed to supernova 1987 amps, where neutrinos and light from an explosion 168,000 light-years away reached Earth within hours of each other. If neutrinos were consistently faster, they should have arrived years earlier. Twitter threads dissected the timing system. Blog posts questioned the GPS synchronization. Some researchers were polite, others blunt. One physicist told Nature the result was probably junk, and publishing it was irresponsible. Opera had measured the travel time by syncing atomic clocks at both ends of the beam using GPS satellites accurate to 10 nanoseconds. The detector sat 1,400 meters underground. The neutrino beam itself was 10.5 microseconds long, but individual neutrino arrivals were time-stamped to within nanoseconds using the proton pulses from CERN. Somewhere in the equipment, a single loose connection was waiting to be found. The team started over. They recalibrated the GPS receivers. They tested the fiber optic cables carrying timing signals between the surface and the underground lab. They borrowed an independent atomic clock and ran comparison checks. In November 2011, they repeated the experiment with shorter neutrino pulses, 3 nanoseconds wide instead of 10,500. The anomaly persisted. In February 2012, an independent experiment called Icarus, using the same beam but a different detector 730 meters away, measured neutrinos arriving exactly at light speed. That's when the opera team knew the problem was theirs. They systematically audited every connection in the timing chain: the master clock, the splitters, the transceivers. 8 kilometers of cable and connectors linking the GPS antenna on the surface to the detector's timing board. It came down to one piece of hardware nobody had thought to check twice. On February 23, 2012, the team found it. A fiber optic cable connecting the GPS receiver to the master clock. The connector had worked itself loose, probably for months. The signal was traveling the correct distance, but the clock was reading it late. The timing error was 73 nanoseconds. The neutrinos had appeared to arrive 60 nanoseconds early. When engineers tightened the connection and reran the beam, the faster-than-light effect vanished completely. 15,000 neutrinos, 3 years of work, 160 scientists, a loose cable. The corrected measurements matched the speed of light within error bars, exactly as predicted. CERN issued a statement on February 24. The world's media, which had spent months debating the end of physics, moved on in less than a week. The fix was simple. The consequences for the people involved were not. Antonio Ereditato, Opera's spokesperson, resigned on March 30th. Dario Altiero, the physics coordinator who'd presented the results, stepped down the same day. Neither had made a mistake in the analysis. They'd done what scientists are supposed to do: report an anomaly, invite scrutiny, remain cautious. But a loose cable isn't a cautious error. It's the kind of oversight undergraduates are warned about. The resignations were voluntary. The damage was already done. Opera published the corrected results in July 2012, confirming neutrinos travel at light speed. Nobody remembers that paper. The incident became a case study in experimental physics courses: how to check your equipment, how to verify a result before going public, how a single overlooked connection can unravel careers and institutional credibility. But the failed experiment left behind a real question nobody had answered. Light is an oscillating wave of electric and magnetic fields regenerating each other as they move through space. No medium required. In a vacuum, every photon travels at exactly 299,792,458 meters per second, regardless of its energy, color, or the motion of its source. That speed isn't arbitrary. It falls out of the equations James Clerk Maxwell wrote in the 1860s, linking electricity and magnetism. The number appears when you combine two constants: electric permittivity and magnetic permeability of empty space. Light speed is baked into the structure of the electromagnetic force itself. But the deeper truth is stranger. Light doesn't just happen to move at that speed. The speed of light defines how space and time relate to each other. It's the conversion factor between distance and duration, the cosmic speed limit written into the universe's operating system. To understand why nothing outruns light, you have to understand what happens to anything that tries. Push any object faster and faster, and Einstein's equations start doing something strange. Its mass doesn't just stay put, it climbs. At half the speed of light, it's barely noticeable, a fraction of a percent. But the closer you creep toward 300,000 kilometers per second, the steeper that curve gets. At 90% of light speed, an object's mass has already more than doubled. At 99%, it's grown sevenfold. Keep pushing, and the number doesn't just get big, it heads toward infinity, which means the energy needed to push it any faster does too. That's the wall. Not a fence you can climb or a door you can force open, but a mathematical dead end built into the fabric of the universe. No engine, no fuel, no amount of energy humanity could ever produce would be enough to cross it. Mass wasn't the only thing relativity warped beyond recognition. High in Earth's atmosphere, cosmic rays slam into air molecules and create particles called muons. These things are unstable. They decay in about 2.2 microseconds. At their speed, that should only give them enough time to travel around 660 meters before vanishing. Yet detectors on the ground pick up muons by the thousand, particles that started their journey 15 kilometers up. They shouldn't survive the trip. But moving at 99.5% of light speed, time itself slows down for them, stretching their 2.2 microsecond lifespan enough to let them reach the surface. It's not just subatomic particles either. In 1971, physicists flew atomic clocks around the world on commercial jets and compared them to clocks that stayed home. The airborne clocks came back out of sync, off by nanoseconds, exactly matching what relativity predicted. That same bending of time created a paradox that confused physicists for decades. Picture two twins. One boards a spacecraft and accelerates to a significant fraction of light speed, off toward a distant star. The other stays home on Earth, living an ordinary life, aging at the ordinary rate. Years pass. The traveling twin turns around and comes home, and when the two finally stand face to face again, they're not the same age anymore. The one who stayed on Earth has aged more, sometimes years more, while their sibling barely aged at all. Here's what makes it a genuine paradox and not just a curiosity. From the traveler's point of view, it's Earth that was moving away and coming back. So shouldn't the Earth-bound twin be the younger one instead? Both perspectives seem equally valid, and yet only one twin actually ages less. The resolution to that paradox hinted at something even stranger waiting past the light barrier. At CERN's Large Hadron Collider, protons get pushed to 99.9999991% of light speed. Getting that last sliver takes an outsized amount of energy, because as an object's velocity climbs, its effective mass climbs with it. Push harder, and the particle doesn't just go faster, it gets heavier, which makes the next push even less effective. The math is brutal. Reaching light speed itself would require infinite energy, more than exists anywhere in the universe. Every accelerator on Earth runs into this same wall, no matter how much power engineers throw at it. For decades, that seemed like the final word. Mass and light speed simply don't mix. Physicists began asking a different question. What if you didn't need to accelerate at all? In 1967, physicist Gerald Feinberg gave a name to a strange idea that had been floating around theoretical circles: tachyons. These would be particles that never slow down to light speed because they start out faster and can never cross into slower territory, just like normal matter can never cross the other way. The logic is almost elegant. Einstein's equations don't forbid faster-than-light particles outright, they just forbid crossing the barrier. A tachyon would simply live on the other side of it, permanently. It sounded like a clever patch, a way to have relativity and speed-breaking travel at the same time. Nobody has ever found one, but that hasn't stopped scientists from taking them seriously. Take the math seriously, and tachyons get stranger. Plug a faster-than-light velocity into Einstein's energy equation, and the result involves the square root of a negative number, an imaginary mass. Physicists don't throw that out. They interpret it. It means the particle's rest mass isn't a real, measurable quantity at all. Some theorists spent entire careers chasing this idea through the 1960s and 70s, running experiments that searched for tiny gaps in arrival times at particle detectors, hoping to catch a tachyon slipping through before its slower cousins. Every search came back empty. And yet the equations kept holding together mathematically, refusing to fully rule the particle out. That consistency is what kept the idea alive for so long. But if tachyons existed, they would break something even more fundamental than speed. Because here's what faster-than-light motion actually threatens: causality itself. In Einstein's universe, the order of events isn't fixed for everyone. Different observers, moving at different speeds, can disagree on which of two events happened first. Normally that's harmless, because nothing can outrun light, so cause always precedes effect for every observer, no exceptions. But send a signal faster than light, and that protection breaks. Some observer, somewhere, would see the reply arrive before the message was sent. Picture a message fired back through a tachyon beam, arriving at its target before it left the sender. A warning that shows up before the danger exists. An effect with no cause behind it yet, just a gap where the reason should be. Physicists call this a closed causal loop, and it's not just strange, it's logically radioactive. It would mean the universe has no consistent story to tell about what happened and why. Some scientists thought they'd found a way around this problem entirely. The workaround starts with a technicality buried in Einstein's own equations. The speed limit doesn't apply to objects. It applies to objects moving through space. Nothing in relativity says space itself has to sit still. Space can stretch, compress, ripple, even expand faster than light, and it already has, during the earliest fraction of a second after the Big Bang. Distant galaxies are being carried away from us right now at speeds beyond light, not because they're moving, but because the space between us is growing. So the loophole isn't about outrunning light at all. It's about changing the racetrack. If you could shrink the space in front of you and stretch the space behind you, you wouldn't be breaking the speed limit, you'd be redrawing the map while standing still inside it. For decades, that stayed a footnote, a curiosity mentioned and set aside. In 1994, one physicist did the math on exactly that idea. His name was Miguel Alcubierre, a Mexican physicist working on general relativity at the University of Wales. He wasn't trying to build a spaceship. He was testing whether Einstein's field equations technically allowed one, and he found a solution nobody had written down before. The idea: wrap a ship in a bubble of flat, undisturbed space. Outside that bubble, contract space-time in front of the ship and expand it behind. The bubble itself would surf that wave, carried along without ever locally exceeding light speed inside its own little pocket of calm. From inside the bubble, you'd feel nothing, no crushing acceleration, no relativistic time dilation, because you're not moving through space in the way the equations restrict. From outside, you'd watch the ship cross light years as if the rules didn't apply to it at all. Alcubierre published the metric, ran the numbers, and checked it against everything general relativity demanded. His equations worked. The problem was what they demanded in return. Run the numbers on Alcubierre's metric and you hit a wall that makes the light barrier look friendly. To warp space enough to carry a ship faster than light, you'd need negative energy on a scale that dwarfs anything in the known universe. Early estimates put the requirement at more energy than the mass of every star, planet, and galaxy combined. Some calculations even pushed past the total mass energy of the observable universe itself. Not a fuel tank, not a reactor, the entire cosmos, converted, and still not enough. Physicists filed the warp drive next to time machines and perpetual motion, mathematically legal, physically absurd. For 20 years, that number seemed to close the door for good. Then, in 2011, a NASA physicist named Harold White went back to Alcubierre's equations and asked a different question. What if the shape of the warp bubble itself was the problem, not the physics underneath it? Alcubierre's original bubble had thick, flat walls. White reshaped it into a thin ring, more like a donut than a soap bubble, and let the space inside pulse rather than sit still. That single geometric change didn't shave off a little energy. It dropped the requirement by multiple orders of magnitude. Suddenly, the number wasn't the mass of the universe anymore. It was something closer to the mass of a spacecraft like Voyager 1, still enormous, but no longer science fiction's punchline. One NASA scientist thought the idea was worth testing in an actual lab. That scientist was White himself, and the lab was real. NASA's Eagleworks Laboratories, tucked inside Johnson Space Center. He wasn't trying to build a starship. He was trying to catch the faintest possible signature of warped space in a controlled experiment on Earth. The setup used a device called a White-Jude warp field interferometer, a modified Michelson interferometer sensitive enough to detect changes in space itself at scales smaller than the width of an atom. If a tiny, contained warp field formed, laser light passing through that region should show a measurable shift. It's the kind of experiment where the equipment costs more attention than the answer does: painstaking, precise, patient. The lab results didn't prove a warp drive worked, but they didn't rule it out either. Alcubierre's math worked on paper, but it demanded something that sounds like science fiction: negative energy density. Not just less energy, but energy density below zero, a region of space where the usual rules invert. For decades, that idea sat in the realm of pure theory, the kind of assumption physicists write down and quietly hope someone else has to explain. Then, quantum mechanics offered a strange gift. The vacuum of space isn't empty. It seethes with fleeting particles popping in and out of existence, and under the right conditions, that churn can produce a patch of negative energy for real. That's not a loophole in the theory. It's a measured, repeatable feature of the universe. Negative energy is real. Getting enough of it is a different story entirely. In 1948, Dutch physicist Hendrik Casimir predicted something bizarre. Take two uncharged metal plates, place them a few micrometers apart in a total vacuum, and they should pull toward each other. No charge, no wind, no obvious force at all. The explanation lives in the quantum foam itself. Outside the plates, the vacuum can fluctuate at every possible wavelength. Between the plates, only certain wavelengths fit, like waves squeezed onto a guitar string. That mismatch leaves less quantum energy between the plates than outside them, and less energy there means negative energy density relative to the surrounding vacuum. In 1997, physicist Steve Lamoureux measured that pull in the lab, and it matched prediction to within a few percent. Scaling that tiny effect up to starship size would take something almost unimaginable. The Casimir effect works because the plates sit nanometers apart. Push them further, and the effect collapses fast, falling off with the fourth power of the distance between them. A warp bubble needs negative energy spread across a region big enough to wrap a spacecraft, not a gap thinner than a human hair. Every calculation for scaling it up runs into walls that don't just bend, they break. Early estimates for an Alcubierre bubble called for negative energy equivalent to the mass of Jupiter, converted entirely and instantly. Even after decades of refinements shaved that number down dramatically, the amount still dwarfs anything humanity has ever harnessed, let alone produced from a quantum vacuum trick measured in fractions of a Newton. No known material, no known process, gets you from a lab bench in Los Alamos to that. Warping space wasn't the only strange idea physicists had for cheating the limit. In 1935, Einstein and a young physicist named Nathan Rosen were trying to smooth out a mathematical wrinkle in general relativity, the ugly point, where a black hole's equations blow up to infinity. What they found instead was a bridge. Their math showed two black holes could be connected by a tunnel through spacetime itself, linking two distant points, or even two different universes. They called it a bridge. Later physicists gave it a friendlier name, a wormhole. The idea sat quietly in the equations for decades, a strange but tolerated consequence of relativity, more curiosity than plan. But if the math was right, the implications were enormous. You wouldn't need to outrun light at all. You'd just skip the distance altogether, stepping through a shortcut stitched into the fabric of space. On paper, a wormhole could get you there instantly. Keeping it open was another matter. Run the numbers on an Einstein-Rosen bridge, and the picture turns grim fast. The moment it forms, the wormhole's throat starts to pinch shut, strangled by its own gravity. It happens in a fraction of a second, far too fast for anything, light included, to cross before the tunnel seals itself off. It's a bit like trying to walk through a door that's already slamming closed the instant it opens. Physicists ran the calculations again and again through the mid-20th century, hoping for an error. There wasn't one. The bridge wasn't a shortcut. It was a trap that closed on itself. For decades, that seemed to be the end of it, a beautiful equation with no practical way through. Wormholes went from a promising loophole to a cautionary tale about what relativity allows and immediately punishes. There was one theoretical fix, and it required something even stranger than negative energy. In 1988, physicist Kip Thorne, working with student Michael Morris at Caltech, published a paper that took the collapsing bridge problem seriously. Their answer was exotic matter, a form of matter with negative mass energy that could, in theory, push back against the wormhole's own gravity. Ordinary matter pulls a wormhole shut. Exotic matter would do the opposite, holding the throat open like a strut wedged into a door frame, resisting the very collapse Einstein's equations predicted. Thorne and Morris showed the physics wasn't forbidden. Nothing in relativity ruled it out outright. It just demanded a substance no one had ever produced, and possibly one that couldn't exist in the quantities needed. Thorne hadn't set out to build a wormhole. He'd been asked a very different question. The question came from Carl Sagan in 1985. He was writing a novel called Contact, about a woman who travels to meet an alien civilization, and he needed a way to get her across the galaxy without breaking the laws of physics he respected so much. So he called his friend Kip Thorne and asked for something that sounded almost like a joke. Could a wormhole actually work? Not as a plot device he could hand-wave away, but as something a real physicist would sign off on. Thorne could have said no. Instead, he went to work, and what he found was that traversable wormholes weren't just permitted by general relativity, they came with a strict, calculable price tag written in exotic matter. The paper he published with student Michael Morris in 1988 was never meant to launch a research field. What started as a favor for a novel became one of the most cited papers in the field. That paper didn't just answer Sagan's question, it opened a door that physicists are still walking through. Traversable wormholes became a legitimate topic in general relativity, studied in the same journals as black holes and neutron stars. Researchers started asking sharper questions. How much exotic matter would you really need? Could quantum effects supply it, even briefly? Could a wormhole stay open long enough to be useful, or would it collapse the instant something tried to pass through? None of these questions existed as serious physics before 1988. Now they sit inside a recognized subfield, built on equations that trace directly back to a novelist's request for scientific plausibility. It's a strange origin story for a field of theoretical physics, fiction asking a question precise enough that reality had to answer it. But wormholes and warp bubbles weren't the only place light speed seemed to bend the rules. Zoom all the way down, past atoms, past electrons, and you find a phenomenon that makes wormholes look almost tame. It's called quantum entanglement, and it starts when two particles are created together in a way that links their properties. Separate them after that, by a room, a continent, or in laboratory tests, by over 1,200 kilometers, and the link doesn't fade. Measure a property of one particle, like its spin, and the other particle's matching property is instantly determined the moment you check it. Not a fraction of a second later, not delayed by the distance between them. The correlation just is, as if the two particles were never really separate at all. Physicists have tested this again and again, closing every loophole they could think of, and the result keeps holding. Einstein himself called it something so unsettling it needed its own nickname. Einstein never accepted it. He'd spent a decade building a universe where nothing outraces light, and here was a theory claiming two particles could sync up instantly across any distance, no signal, no delay, no travel time at all. In 1935, he and two colleagues wrote a paper trying to break entanglement, arguing quantum mechanics had to be missing something, some hidden instructions set the particles carried with them. He called the apparent effect spooky action at a distance, and he meant it as an insult. For decades, it stayed a thought experiment, until physicist John Bell worked out a way to actually test it in 1964. Labs spent the next 50 years running that test, and in 2015, Dutch researchers finally closed every remaining gap, measuring entangled particles 1.3 kilometers apart, with no room left for hidden signals. The experiments proved entanglement was real. What they proved about speed was more complicated. Here's the catch nobody expects. Measure one entangled particle and its partner's state locks in instantly. But the person holding that partner has no way to know a measurement even happened. Their particle just looks random, spin up or down, 50-50, same as any unmeasured particle would. Only when the two people compare notes later, over an ordinary phone call or email, moving at or below light speed, does the correlation show up at all. Physicists call this the no communication theorem, and it's been proven mathematically from the core equations of quantum mechanics itself. You cannot encode a message in entanglement, no letters, no bits, nothing. The universe hands you a locked connection and keeps the key just out of reach. One more quantum trick seemed to promise a way around the limit. It didn't survive scrutiny either. In 1993, physicist Raymond Chiao ran an experiment that seemed to break the rules outright. He fired photons at a barrier they shouldn't have been able to cross, a quantum tunneling setup, and clocked some of them getting through faster than light speed would allow for that distance. Later experiments pushed the numbers further. A 2020 University of Toronto study measured tunneling photons crossing an 1.4 micrometer barrier in a time that implied speeds up to 1.68 times light speed. But what gets measured in these experiments isn't a photon traveling a path, it's a probability wave reshaping itself and pinning down exactly when a photon arrives inside a quantum tunnel is far messier than clocking a sprinter. Physicists still argue about whether the effect is a real speed violation or a trick of how the measurement itself is defined. The debate over what those experiments really proved is still not fully settled. There's one exception so big it dwarfs every lab experiment we've talked about. In the first fraction of a second after the Big Bang, space itself expanded faster than light. Not particles, not signals, not spacecraft, the fabric of the universe. Physicists call it inflation, and the numbers are almost absurd. In roughly 10 to the negative 32 seconds, the universe is thought to have doubled in size, dozens of times over, stretching a region smaller than an atom into something the size of a grapefruit or larger. That's an expansion rate that makes light look sluggish by comparison. And yet not a single law of physics got broken doing it. That wasn't a loophole. It was a completely different rule most people never learn. Here's the rule. Einstein's speed limit applies to things moving through space, like a ship, a signal, a beam of light crossing from one point to another. It says nothing about space itself stretching. And that's not just a theory tucked away in equations. Astronomers see it happening right now. Galaxies far enough away from us are receding faster than light, not because they're flying through space, but because the space between us and them keeps growing. Edwin Hubble first noticed distant galaxies rushing away back in 1929, and the further out you look, the faster the recession gets. Push that relationship out far enough, and you cross the light speed line without anything ever actually moving that fast. That distinction was about to become the key to everything happening back at mission control. Push the math out to about 14 billion light-years and you hit something strange. Galaxies out there are receding from us faster than light itself travels, not as a hypothetical, but as a measured consequence of how expansion works. It means there are galaxies whose light will never reach us, not because they're too dim, not because our telescopes aren't good enough, but because the space between here and there is growing faster than their light can close the gap. They're outrunning us permanently. That boundary has a name, the cosmological horizon. Everything beyond it isn't just far away, it's causally cut off, drifting further out of reach with every second that passes. If space itself could move that fast, some physicists wondered if a ship could ride along. Miguel Alcubierre's 1994 paper had proposed a workaround. Don't push the ship through space, warp the space around it. Contract space-time ahead of the vessel, expand it behind, and let the ship ride the wave like a surfer on a cosmic ocean. Inside the bubble, nothing moves faster than light relative to local space. The math worked. You'd compress kilometers of space in front into centimeters, stretch centimeters behind into kilometers, and the ship would slide forward, without ever accelerating. No violation of special relativity because the ship itself stays stationary inside its own reference frame. The universe moves around you instead. The problem was energy. Alcubierre's equations demanded exotic matter with negative mass energy, something that bends space-time the opposite way normal matter does. Nobody's ever found it, and most physicists doubt it exists in macroscopic quantities. For 25 years, the warp drive stayed a beautiful piece of mathematics with no physical path forward. Then cosmologists remembered, space already expands faster than light at the universe's edge, powered by nothing exotic at all. In the years since Alcubierre's paper, a new generation of physicists picked up where he left off. In 2021, Eric Lentz at Göttingen published equations for a warp drive using only positive energy, no exotic matter required. He used solitons, self-reinforcing wave packets that hold their shape, to create the space-time distortion. The energy demand dropped from Jupiter mass to something closer to a large planet, still absurd but no longer mathematically impossible. Then in 2024, Jared Fuchs and his team refined the geometry further, cutting the requirement to roughly the mass of a large asteroid. They flattened the warp bubble's shape, stretched it into an elongated shell, and found configurations that stayed stable without collapsing. Other groups found solutions that didn't violate causality or quantum field theory's known constraints. The models kept improving. Researchers discovered you could tune the bubble's thickness, its velocity profile, even sandwich multiple geometries to cancel out destabilizing effects. Every paper brought the energy budget down another order of magnitude, inching towards something that might one day be engineered rather than merely calculated. A positive energy warp drive sounded like the breakthrough everyone had been waiting for. Except the new models solved one problem and quietly introduced another. The equations described how to maintain a warp bubble moving at constant velocity, even superluminal velocity, using realistic physics. What they didn't show was how to accelerate the bubble from rest to faster than light in the first place. You can't build the bubble around a stationary ship and then push it to warp speed, because pushing it requires moving energy and information faster than light to get there. You'd need the warp drive to already be working before you turn it on. Lentz's paper acknowledged this. His solitons could travel at any speed you configure them for, but transitioning between speeds remained an open question. Some proposals suggested building the bubble far from the ship, letting it pass through at whatever speed you'd designed it for, then somehow capturing the vessel inside. Others hoped future refinements might find a way to bootstrap the acceleration from within. But as of 2026, no published model had closed the loop. The math was gorgeous, the energy requirements were dropping, and nobody knew how to actually turn the thing on. If warping space wasn't the answer yet, some scientists asked whether getting close to light speed might be enough. You wouldn't need to break the speed limit to break your brain. At 99% of light speed, time itself would start bending for you. A trip that takes a distant observer years would feel like weeks, days, maybe less, depending on how close you pushed it. This is time dilation, and it's not theoretical. GPS satellites already correct for a tiny version of this effect every single day, just from moving a few kilometers per second. Push that speed toward 99% of light, and the correction stops being tiny. Your clock would keep ticking normally to you. Everyone back home would just be aging faster in comparison. At that speed, the universe wouldn't just move faster, it would start to look completely different. Point a camera out the front window at relativistic speed, and the stars wouldn't sit where they're supposed to. They'd start sliding forward, crowding into the direction of travel, like the whole sky was being funneled through a lens. Physicists call it the aberration of light. Light from stars off to the side would appear to bend toward your heading, and light from behind would thin out, stretching into the space you left behind. Push past 90% of light speed, and the effect gets extreme. Nearly the entire visible sky would compress into a bright circle directly ahead, a kind of tunnel of starlight, while the rest of the universe fades to black around it. Color itself would stop behaving the way it always had. Every star inside that forward tunnel would also be shifting in color. This is the relativistic Doppler effect, the same principle that changes a siren's pitch as it passes you, except now it's happening to light instead of sound. Light waves ahead of the ship get compressed, pushed toward shorter wavelengths. Red stars would start looking white. White stars would edge toward blue. Push the speed high enough, and visible light itself would shift straight out of the visible range. At extreme fractions of light speed, that forward starlight wouldn't just look blue. It would shift into ultraviolet, then X-rays, then gamma radiation, the most energetic and dangerous light in the universe. Behind the ship, the opposite was happening, and it was just as strange. Behind the ship, every star the crew had left was stretching in the other direction. Redshift took over back there, pulling light down the spectrum instead of up it. The engines glowing white one moment would drift toward orange, then deep red, then nothing at all. Whole constellations would fade out of view, not because they'd gone anywhere, but because their light had been stretched past what human eyes could catch. Look back at the galaxy you came from, and eventually you'd see empty black where a sky full of stars used to be. The rear view would go dark long before the journey was over. It's a strange kind of isolation, watching your own history disappear photon by photon. But the view was the least of the crew's problems. Space isn't empty. It's full of stray hydrogen atoms, dust grains, and the leftover microwave radiation from the Big Bang itself, drifting at random, going nowhere in particular. At normal speeds, none of that matters. A ship gliding through the solar system barely notices it's there. But push a spacecraft to a large fraction of light speed, and that same faint radiation gets blue-shifted, compressed into far higher energy by the ship's own velocity. The cosmic microwave background, a chilly 2.7 K glow that fills all of space, would blast the hull like hard X-rays. Even a single dust grain, hit at relativistic speed, carries the punch of a small explosive. Sustained exposure like that doesn't just damage electronics. It cooks a hull from the outside in. Any ship attempting this would need protection nobody has built yet. Engineers have floated a few real answers to that problem, none of them simple. One idea borrows from Earth's own defenses: generate a powerful magnetic field around the ship to deflect charged particles. The same trick our planet's magnetosphere uses against solar wind, just scaled up and turned outward. Another approach is more brute force. Pack a thick layer of ice or metal at the bow, a sacrificial shield that erodes as it absorbs impacts, slowly ablating away over the course of the voyage like a heat shield on re-entry, just stretched across years instead of minutes. Some proposals even combine both, a magnetic screen to handle charged particles and a physical shield for the neutral debris that magnetism can't touch. On paper, they buy survivability. Even with perfect shielding, one problem couldn't be engineered away. So the ship survives the debris. Now it has to actually get up to speed, and that's where the math turns brutal. To reach even half the speed of light using conventional rocket fuel, a ship would need to carry more propellant than the observable mass of a small moon, and most of that fuel would be spent accelerating the fuel itself. It's called the tyranny of the rocket equation. Every kilogram of payload demands exponentially more propellant, which adds more mass, which demands even more propellant. Chemical rockets top out around 5 kilometers per second. Ion engines can push past 100 kilometers per second over years, but that's still a fraction of a percent of light speed. Nuclear pulse designs and fusion drives close the gap, but none of them scale to a crude interstellar mission without tanks the size of asteroids. For decades, this was the wall that stopped every serious proposal cold. One real project tried to sidestep the fuel problem completely. In 2016, physicist Yuri Milner and Stephen Hawking announced breakthrough Starshot, backed by roughly $100 million in early funding. The idea was radical. Stop carrying fuel altogether. Leave the engine on the ground. The plan calls for a fleet of probes, each one the size of a smartphone chip and weighing just a few grams, attached to a thin, reflective sail. Instead of burning propellant, the probe would be pushed by light itself, blasted from an array of ground-based lasers with a combined output over 100 gigawatts. The target is Alpha Centauri, our nearest star system at 4.24 light-years away. At the speed Starshot is chasing, a probe could make the crossing in about 20 years instead of tens of thousands. The concept sounded almost too simple. The engineering behind it was anything but. Light doesn't have mass, but it carries momentum, and when photons strike a surface, they transfer a tiny push. It's the same principle behind solar sails already tested in orbit, just scaled up to an extreme. Aim a laser powerful enough at a sail light enough, and that whisper of pressure becomes real acceleration. Starshot's sail is designed to be only a few atoms thick, a meter or so across, and reflective enough to survive a beam strong enough to vaporize steel. Under that laser array, the math says the probe could reach 20% of light speed in just minutes of acceleration, then coast the rest of the way in silence. No fuel tank, no engine, just a sheet of material riding a beam of light across interstellar space. Getting the concept to work in theory was one thing, getting it built was another. In 2016, Yuri Milner pledged $100 millions to get this off the ground, with Stephen Hawking and Mark Zuckerberg standing beside him at the announcement. Nearly a decade later, researchers who worked on the project say only about $4.05 million of that ever actually got spent, spread across roughly 30 small contracts for laser arrays and sail prototypes. One physicist at the University of Sydney told reporters his team simply stopped working when the funding dried up, and he never heard from breakthrough initiatives again. By 2025, people close to the project were describing it as being on indefinite hold, with no announcement, no press release, just silence. The 100-gigawatt laser array the concept depends on would need power output rivaling hundreds of nuclear plants running at once, and nobody has solved that at scale. The original timeline pointed to a possible launch around 2036. That date is looking further away every year. None of this explained what Mission Control had actually seen on their screens. Back on that ship, the clock on the control panel was still ticking, just not in sync with anything on Earth. Every second it logged should have matched a second back home. It didn't, and the gap between the two kept growing the longer the mission ran. Mission Control had flagged the anomaly hours earlier, then watched it get worse instead of resolving itself. Nobody on the ground could explain why a piece of hardware that had worked flawlessly in testing was suddenly disagreeing with reality. The crew reported nothing wrong. The instruments insisted otherwise. That kind of mismatch doesn't happen because of a broken part. It happens because of what the ship was doing to get where it was going and how fast it was doing it. To understand what that ship was actually doing, the story has to go back to how it got there. Picture a spacecraft built not from speculation, but from equations physicists already trust, the same relativity that predicts GPS drift and particle decay. No warp drive, no shortcuts through space itself, just a vessel pushed hard enough, long enough to approach a meaningful fraction of light speed. That's the thought experiment worth running in full. Not a 5-minute sci-fi montage, but a mission profile with real numbers attached. How much energy it would take, how the crew would experience time differently from everyone they left behind, and what the universe outside the window would actually look like at those speeds. Every stage of that voyage traces back to physics that's already been tested in labs and particle accelerators here on Earth. The first stage of that journey alone would test everything scientists know about propulsion. Project Orion, drawn up in the late 1950s, proposed pushing a spacecraft forward by detonating nuclear bombs behind it, one after another, riding the shockwaves like a surfer catching endless waves. On paper, it could reach a few percent of light speed. Even at that pace, a trip to Proxima Centauri would take over 100 years, longer than the lifespan of anyone aboard. Project Daedalus, designed by the British Interplanetary Society in the 1970s, swapped bombs for fusion pellets ignited by electron beams, aiming for about 12% of light speed. That still meant a 50-year one-way flight to a nearby star, with no way to slow down and no way to turn back. Every proposal ran into the same wall. Getting to relativistic speed takes decades even in the best-case math, and stopping takes just as long. Fuel efficiency became the whole game, and one fuel promised more energy per kilogram than fusion, than fission, than anything chemical rockets could ever touch. One of those proposals used a fuel more powerful and more dangerous than anything else on the list. Antimatter is the closest thing physics has to a perfect fuel. When matter and antimatter collide, they don't just react, they annihilate completely, converting 100% of their mass into pure energy. Compare that to a nuclear reactor, which taps less than 1% of its fuel's mass energy, and antimatter starts to look like science fiction made real. A ship powered by antimatter could, in theory, reach speeds no fusion drive ever could, hauling far less fuel for far more thrust. Engineers have run the numbers, and the physics checks out. It's the logistics that fall apart. Antimatter can't be mined or drilled or harvested anywhere in the solar system. It has to be manufactured, one particle at a time, in machines built for research, not rocket fuel. And it has to be stored without ever touching a single atom of ordinary matter, or it detonates on contact. The actual amount of antimatter humanity has ever created would fit almost nowhere. At CERN, the only place on Earth producing antimatter in meaningful research quantities, scientists have been making antiprotons since the 1980s. Add up every antiproton CERN has ever created, across 4 decades of experiments, and the total mass comes out to a few billionths of a gram. That's not enough to power a light bulb for more than a moment, let alone a starship, and the price tag matches the scarcity. Estimates have put the cost of producing a single gram of antimatter at well over $1 trillion, making it, gram for gram, the most expensive material humans have ever manufactured. A starship built on Daedalus-style specs would need tons of antimatter fuel, not billionths of a gram. At CERN's current output, filling that tank wouldn't take years. It would take longer than civilization has existed. Assume for a moment that a crew found a way past every one of these obstacles. On board, the crew wakes up, eats breakfast, checks instruments. Coffee still pours down instead of sideways. Conversations still take the same beat to land. Laughter still arrives right on cue. Their hearts still beat at a normal pace, at least to them. Their thoughts don't stretch out or speed up. If you handed one of them a stopwatch, it would tick exactly the way it always has, 1 second at a time, no different than back home. That's the strange part. There's no sensation of speed here, no wind, no rumble, no sense of the ship straining against anything. Near light speed doesn't feel like anything at all from inside the hull. From inside the ship, none of it would feel unusual. From outside, everything would. Run the math on a ship holding 99.5% of light speed. The Lorentz factor at that speed comes out to about 10. For every year that ticks by on the ship's clock, roughly 10 years tick by back on Earth. Push it further to 99.99%, and that factor jumps past 70. A 5-year voyage by the crew's own calendar becomes 350 years for everyone they left behind. The faster the ship pushes toward light speed, the more violently that ratio bends. This isn't speculation or rounding error. It's been measured directly, in muons screaming through the atmosphere and in atomic clocks flown on jets, both matching Einstein's equations to remarkable precision. The physics is settled. What's unsettling is watching it applied to a human timeline. That gap between the two clocks was exactly what Mission Control was staring at. Picture the crew stepping off that ship after what felt, to them, like a routine multi-year run. For the people waiting on the ground, it wouldn't be years, it could be generations. The children of the engineers who launched them would be old. the mission's original planners would be gone. Buildings near the launch site might be demolished and replaced twice over. Technology unrecognizable. Entire political borders redrawn. The crew wouldn't have aged into that world gradually, the way everyone else did, absorbing change year by year. They'd arrive into it all at once, a hard cut from one era to another, still wearing the faces and habits of the world they left. Decades might pass easily, but what if the gap were far, far larger? Push the velocity higher, past 99%, up toward 99.9999% of light speed, and the math stops being gentle. At that speed, time dilation isn't a factor of 2 or 10 anymore. It's a factor of hundreds, then thousands, depending on how close you get to the wall you can never actually touch. A crew living through a single year on board, eating meals, running diagnostics, sleeping in shifts, could return to find that centuries had passed back home. Not decades, centuries. Empires could rise and fall in the space between breakfast and a birthday. This isn't science fiction license. It falls straight out of the same equations that already run inside every GPS satellite orbiting Earth right now, just scaled up to a speed no human craft has ever reached. At that point, the question stops being about speed and starts being about time itself. Which brings us back to that string of timestamps Mission Control couldn't explain. A signal logged as arriving before it was sent. A clock on the spacecraft that seemed to be running on its own private schedule, disagreeing with every ground station tracking it. For years, the assumption was equipment failure, a bad oscillator, a corrupted timestamp, something boring and fixable. But boring explanations kept failing to account for the pattern because the drift wasn't random. It was consistent, growing, and it matched something. It matched exactly what you'd expect if that spacecraft had spent part of its mission moving fast enough for relativity to stop being a rounding error and start being the whole story. The full picture of what that spacecraft had actually done was about to come together. But a split clock raises a darker question than Mission Control ever wanted to deal with. If time can run at different rates for two observers, one on the ship, one on Earth, then order itself gets slippery. Which event actually happened first stops being a simple question. Physicists have a name for the nightmare version of this: causality violation. Effects arriving before their causes, signals answered before they're sent. It sounds like a glitch in a simulation, not a property of the universe we're actually standing in. Einstein's own equations don't rule it out cleanly, not at every extreme. And once you let that door crack open even slightly, you're standing right next to one of the oldest, strangest problems in all of physics. One thought experiment was about to turn this abstract oddity into a genuine crisis for physics. Picture your ship crossing that threshold, moving faster than light itself. To an observer watching from Earth, something breaks. The order of events, cause, and then effect, starts to scramble depending on where you're standing. Run the math and you get a signal that arrives before it was sent, not metaphorically, literally earlier, on someone else's clock. Chain a few of these faster-than-light hops together, bouncing a message between two ships in relative motion, and you can construct a loop that ends right back at its own beginning. That's the moment this stops being a curiosity about clocks and becomes something else entirely, a message reaching the past, a warning that arrives before the disaster, a version of you finding out something you haven't done yet, because in someone else's frame, you already have. There was a reason most physicists weren't losing sleep over this, and it had to do with a rule nobody could break. In the 1990s, Stephen Hawking looked at exactly this kind of loophole and proposed something almost defensive on nature's behalf. He called it the chronology protection conjecture. The idea, the laws of physics actively prevent closed loops in time from ever forming, no matter how clever the setup. Hawking put it bluntly. He said it seemed like there ought to be a law protecting history from tourists, since we don't see the past overrun with visitors from our future. No grandfather paradoxes playing out, no contradictions littering the timeline. It's a strange kind of law, though, because nobody could point to the mechanism enforcing it. not a particle, not a force, not an equation with a name. Just a suspicion that whenever the math tries to build a time loop, something in the universe steps in to shut it down first. But conjectures aren't proof, and the universe would need to show its hand. By the mid-90s, physicists had a candidate for that enforcer, and it came from an unlikely place, the jittery, ever-fluctuating vacuum of empty space itself. Quantum field theory says a true vacuum is never perfectly still. Particles and antiparticles wink in and out of existence constantly, borrowing energy and paying it back almost instantly. Calculations by physicists like Kip Thorne and Matt Visser suggested something dramatic happens near a closed time-like curve. Those quantum fluctuations don't stay small. They start to loop back on themselves, feeding on their own reflections, and the energy density can spike toward infinity, right at the spot where the time loop would form. In effect, the universe doesn't need a cosmic censor with a rulebook. The geometry punishes itself. Any structure trying to bend space-time into a loop gets torn apart by its own runaway vacuum energy before the loop ever closes. No lab could recreate that condition, but something in deep space already might. Roger Penrose ran into the same wall decades ago. His math kept producing naked singularities, points of infinite density with nothing hiding them from view, and physics doesn't like to show its infinities in public. So he proposed cosmic censorship. The universe always wraps a singularity in an event horizon, sealing it off before it can break anything outside. No one has proven it, but every black hole we've ever measured obeys the rule. Kip Thorne made a related bet with Stephen Hawking on exactly this question and mostly lost. Nature keeps closing the loopholes almost as fast as theorists find them. It looks less like an accident and more like a pattern, a system with rules that quietly enforce themselves. And that same self-protection instinct in the cosmos was about to reappear in the most unlikely place. Back on the ship, the forward sensors start acting up. At 80% of light speed, the navigation display shows familiar constellations, but they're crowding together in ways no star chart predicted. The crew runs a diagnostic. Every system checks out green, no hardware fault, no calibration drift, nothing a reset would fix. Push past 95% and the effect gets worse. Stars that should sit far to either side of the ship's heading are sliding toward dead center, piling up into a bright smear the instruments can barely resolve. The onboard AI flags it as a sensor anomaly, because that's the only category it has for something like this. Something was warping their picture of space itself, and it wasn't a malfunction. It's an old effect with a new intensity, aberration of light. Even Earth's own orbital speed, a mere 30 kilometers per second, shifts the apparent position of every star by a tiny, measurable angle, something astronomers have tracked since the 1700s. Crank that speed up toward light itself, and the shift stops being subtle. Photons arriving from the side get swept forward in the ship's frame, the same way rain looks like it's coming from ahead when you run through it. At 99.9% of light speed, the math collapses almost the entire sky into a narrow cone dead ahead. Stars that were behind the ship, beside it, even slightly to the rear, all get dragged into that forward patch of sky. From inside the cockpit, the universe stops looking like a sphere of scattered points and starts looking like it's funneling into a single, blinding well of light. Ahead was a tunnel of light, but what was happening behind the ship was even stranger. Look the other way, and the picture flips entirely. Any light trying to catch the ship from behind has to outrun something moving close to sea, and it simply can't close the gap fast enough to register as a normal star anymore. The wavelengths stretch out past red, past infrared, down into frequencies human eyes were never built to catch. So the rear window doesn't show retreating stars fading into the distance the way you'd picture it. It shows nothing, a flat, total black, with no texture, no depth, no pinpricks of light to judge speed or distance by. Every window facing forward is overloaded with a blinding funnel of compressed starlight, and every window facing aft is an empty void. There's no gentle gradient between the two, just a hard seam where the universe simply stops. Living inside that optical trap for months would do something to a person that no simulation had fully modeled. Mission psychologists had seen versions of this problem before, just not at these extremes. The closest real data came from programs like Mars 500, where 6 crew members spent 520 days sealed inside a mock spacecraft in Moscow with no real windows at all. The results were mixed but telling. Sleep-wake cycles drifted, 4 of the 6 crew developed disrupted sleep patterns, and 1 participant reported depressive symptoms in over 90% of the mission's weeks. Researchers also noted a strange side effect in confined subjects, a measurable loss of depth perception after prolonged exposure to restricted visual environments. Now stretch that same deprivation over a starship crew staring at a bright funnel ahead and a light-eating void behind, for a voyage lasting years instead of months. Psychologists flagged this as a genuine risk to judgment and mood long before liftoff. There was a fix on the table, but it came with its own trade-off. The engineering solution didn't try to change the physics because the physics wasn't negotiable. Instead, it aimed the fix at the display. Strip out the direct viewports and replace them with cameras feeding into onboard processors that could digitally correct the image in real time. The computer would take the compressed, blue-shifted mess pouring in from the forward sensors, run it back through the aberration and Doppler math, and reconstruct something closer to what the sky would look like if the ship were sitting still. Individual stars, spread out, back in their familiar positions, instead of one violent smear of light. It sounded like a clean patch, restoring a normal-looking sky for the crew's sanity. But every correction the computer applied to make the view feel human was a correction subtracted from the raw data underneath. Fixing what the eyes saw meant sacrificing what the instruments could measure. Some engineers on the design team argued the fix was worth it no matter the cost. A crew staring into a warped, colorless void for years on end wasn't just uncomfortable, it was a mental health risk that could end a mission long before any star system came into view. Others pushed back hard. Every smoothing algorithm was a layer between the astronauts and reality was the entire point of sending people instead of just instruments. Strip away too much of the raw signal, and you've built an expensive, crude camera that sees less than an uncrewed one would. No side won that argument on paper. Different mission concepts landed in different places, some favoring the softened view, some favoring the truth, unfiltered. But comfort and data weren't the only things at stake out there. Space is not empty. It only looks that way from a planet's surface, where the atmosphere hides just how much stuff drifts between the stars. Out past the heliosphere, the galaxy is filled with a thin, ghostly mix of hydrogen atoms, helium, and fine grains of dust, the leftover material from stars that lived and died long before the sun ever formed. At rest, this stuff is almost nothing. A hydrogen atom here, a speck of dust there, spread so thin that a cubic centimeter of interstellar space might hold less than 1 atom. Ships have always passed through it without a second thought. A relativistic starship doesn't get that luxury. At a meaningful fraction of light speed, the ship isn't drifting through that thin haze anymore. It's slamming into it, thousands of times a second. A single grain of dust was about to become one of the most dangerous objects in the galaxy. Kinetic energy scales with the square of velocity, which means speed matters far more than mass ever could. A dust grain weighing a fraction of a milligram, something you could lose in a fingerprint, barely registers as a threat sitting still. Push it to 90% of light speed, and the math changes completely. At those velocities, relativistic effects pile on top of ordinary physics, and the grain's effective mass climbs as it approaches the speed of light. The result is a particle smaller than a period on this screen, striking the hull with the energy of a stick of dynamite, sometimes more, depending on the closing speed and the grain's size. Multiply that by every grain in the ship's path over a multi-year crossing, and you have a slow bombardment capable of sandblasting through hull plating or ending a mission in a single unlucky impact. Someone had already tried to solve this exact problem, decades before anyone seriously planned a starship. NASA engineer Fred Whipple solved a version of this problem back in 1946, decades before anyone drew up a starship blueprint. His idea was simple: put a thin sacrificial layer a few centimeters ahead of the main hull and let incoming debris shatter against it, vaporizing into a harmless spray before it ever reaches the real structure. It worked. Whipple shields still protect the ISS today, shrugging off flecks of orbital debris moving at 7 kilometers a second, but run the same design at 90% of light speed, and the numbers stop cooperating. At orbital speeds, a shield has to survive an impact. At relativistic speeds, that same grain of dust carries roughly 10,000 times the kinetic energy, enough to punch straight through meters of shielding like it wasn't there. Stack on more layers, and you just add mass, which demands more fuel, which was already the problem nobody could solve. The old shields failed the math, so engineers went looking for something stranger. One idea skips solid material entirely. A magnetic sail, essentially a giant superconducting loop wrapped around the ship, would generate a field strong enough to deflect charged particles before they ever reach the hull. It's the same principle that shields Earth from the solar wind, scaled up and pointed forward. The trouble is that most interstellar dust isn't charged. Neutral grains sail straight through a magnetic field like it isn't there, which means the sail only stops part of the threat. Another proposal swaps steel for ice. A disposable shield of frozen water or hydrogen, kilometers thick in some concepts, absorbs and vaporizes impacts, then gets slowly eroded away and replaced over the voyage, like a windshield sacrificing itself one chip at a time. Some designs even suggest firing a cloud of ablative particles ahead of the ship, detonating incoming grains before they close the final distance. Every proposed fix ran into the same wall: the sheer amount of energy required. Generating a magnetic field wide enough to matter takes power. Vaporizing ice fast enough to keep pace with a ship crossing light years takes power. And every kilogram of shielding, sacrificial or otherwise, is dead weight the engines have to drag along at relativistic speed, which means more reaction mass, which means more fuel. This is the same ledger that showed antimatter propulsion needing more energy than humanity has ever produced just to reach a meaningful fraction of light speed. Now add a defense system that has to run continuously for years, without failure, protecting a hull that can't afford a single unlucky hit. The propulsion budget and the shielding budget aren't separate problems. They draw from the same finite pool of energy, and every gram spent on one is a gram taken from the other. Every problem in this voyage kept circling back to the same brutal equation. So somebody finally sat down and did it properly. Take the propulsion energy needed to reach a meaningful fraction of light speed. Add the shielding mass needed to survive that speed. Add decades of life support, radiation shelters, redundant systems, everything a real crew would need to stay alive. Then run it all through the same relativistic equations, because at these velocities, nothing is free and nothing is separate. Fuel, shielding, and food all draw from the same pool of joules, and that pool has a bottom. Engineers stacked every requirement into a single number and started doing the arithmetic. What came out the other side wasn't just big. It was the kind of number that makes you double-check your math, then check it again. That number, once physicists actually wrote it down, changed how they talked about interstellar travel entirely. Accelerating a modest starship to even half the speed of light, with shielding included, takes something on the order of 10^32 joules. For comparison, that's roughly what the sun radiates into space every few seconds, scaled up to power a single spacecraft for its whole journey. Humanity's entire annual energy consumption doesn't even register as a rounding error next to it. Push the ship closer to light speed, and the number climbs faster than intuition can follow. because relativistic mass increase means every added joule buys less and less speed. You're not just fighting distance anymore. You're fighting a universe that gets more expensive to move through the harder you push. This is why, with the propulsion technology sitting in labs right now, a crude relativistic starship stays firmly on paper. Faced with numbers like that, some scientists didn't retreat, they got creative. In 1960, physicist Freeman Dyson floated an idea that sounds like science fiction until you look at the math behind it. Instead of building a bigger rocket, build a structure that captures a star's entire energy output. Not a fraction of it, all of it, funneled and stored for use. Dyson didn't imagine a solid shell wrapped around a sun. That idea came from later interpretations. He described a swarm, countless collectors in independent orbits, harvesting sunlight the way a solar panel does, just at a scale that dwarfs every planet in a system combined. A single star like our Sun outputs about 3.8 times 1046 watts every second. Even a fraction of a Dyson swarm's output would dwarf the total energy budget interstellar travel demands, at least on paper. Even with a star's worth of power, one obstacle refused to go away. But energy was never the only bill on the table. A Dyson swarm capable of powering a starship isn't something you bolt together in a weekend. Estimates for even a modest version, a partial ring of collectors around the Sun, run into centuries of construction, and that's assuming we started tomorrow with unlimited resources. Some models push the full timeline past 1,000 years, depending on how fast you can mine, manufacture, and launch material into orbit. No person alive today would see it finished. No person alive when it's finished would remember who started it. So the math worked on paper, but paper doesn't board a spacecraft. That question of who actually makes the trip was about to get a very different kind of answer. If a project spans centuries, the obvious fix is to stop assuming a human has to be awake for it, or even alive for it. Engineers started sketching a different kind of traveler altogether. Unmanned probes, boosted to a meaningful fraction of light speed, with no life support, no food, no crew quarters eating into the mass budget. Strip out everything a human body needs, and the ship gets lighter, faster, and dramatically cheaper to accelerate. Breakthrough Starshot, proposed in 2016, imagined wafer-thin probes the size of a microchip, pushed by ground-based lasers to roughly 20% of light speed, reaching Alpha Centauri in about 20 years instead of tens of thousands. No astronaut has to survive re-entry because there's no re-entry, and no astronaut has to survive the trip because there's no astronaut. If humans weren't going, then something else had to decide what was worth finding. A probe like this doesn't get a return leg. At a real fraction of light speed, turning around and decelerating would cost as much energy as the entire outbound journey. So the mission is one way by design, not by accident. Whatever it finds, it reports home, and then it just keeps going, forever, into whatever's past the target. That's a strange kind of machine to build. You're engineering something meant to outlive the people who built it, transmit for a few minutes after a years-long silence, and then drift, powered down, past a star system it took decades to reach. There's no rescue plan, no software update, no second chance if a single component fails at 20% of light speed. Somewhere out there, mission planners had already picked their first target. That target was Proxima Centauri, the closest star to our Sun, sitting just over 4 light-years away. At 20% of light speed, a probe could cross that gap in roughly 20 years, close enough to matter within a human lifetime. Proxima is a small red dwarf, dimmer and cooler than the Sun, but it turns out to have a planet orbiting inside its habitable zone. Astronomers named it Proxima b, and it's roughly the mass of Earth. A rocky world, the right temperature range for liquid water, circling the nearest star in the sky. That planet hadn't always been on anyone's map, and how it got discovered was a story of its own. You can't just point a telescope at Proxima and see a planet sitting there. It's too small, too dim, too close to the glare of its star. Astronomers had to find it by watching the star wobble instead. A planet's gravity tugs its star back and forth slightly as it orbits, and that motion stretches and compresses the light reaching us, a shift known as the radial velocity method. Researchers tracked Proxima's light for years, sifting a signal a few miles per hour out of noisy data. In 2016, a team using that method, part of the Pale Red Dot project, confirmed the wobble matched a planet orbiting every 11 days. Confirming the planet existed was one thing. Figuring out if anything could survive there was another. Being in the habitable zone sounds promising until you look at what kind of star Proxima actually is. Red dwarfs are small, but they're temperamental, prone to sudden, violent flares, far more intense relative to their size than anything our Sun produces. And because Proxima b orbits so close, just 5% of the distance between Earth and the Sun, it sits directly in the blast radius. A flare that would barely register from our Sun could scour that planet's atmosphere from just a few million miles away. That's not a hypothetical risk. Astronomers have already caught Proxima in the act. One flare in particular showed scientists just how violent this neighboring star could get. On May 1st, 2019, 5 different observatories were watching Proxima at once. Radio dishes, a space telescope, ground-based scopes, all trained on one small red star, just in case. And then it happened. A flare tore off the surface that was roughly 100 times more powerful than anything our own Sun has ever produced. For a few seconds, Proxima brightened by a factor of 14,000 in ultraviolet light. Researchers who studied the event said a person standing on that planet would have a very bad time. This wasn't a one-off either. Evidence suggests Proxima's planets get hit by something this violent not once a century, like on Earth, but possibly several times a day. Radiation like that can strip ozone from an atmosphere in years, not eons. Model runs suggest a flare this size could erode 90% of an Earth-like ozone layer in just 5 years of repeated hits. Whether Proxima b had any atmosphere left at all was still an open question when the data came in. Some scientists point to a possible lifeline. A strong planetary magnetic field could, in theory, deflect the charged particles before they ever reach the air. Earth's field does exactly that against our Sun's outbursts. And if Proxima b generates something similar, its atmosphere might survive far more punishment than a bare rock ever could. But other models tell a darker story. Proxima b orbits its star roughly 20 times closer than Earth orbits the Sun, just to stay warm enough for liquid water. That proximity means any magnetic shield would need to be extraordinarily strong, and there's no direct evidence yet that Proxima b has a magnetic field at all. So the two pictures just sit there, unresolved, a shielded world that kept its air, or a sterile husk scoured clean billions of years ago. Nobody could settle it with the instruments on hand in 2019, and simulations alone can only narrow the odds. One instrument, still years from launch, was built specifically to settle this argument. You don't have to send anything to Proxima to get an answer. You just need to see it, which sounds almost too simple, except blocking out a star to spot a planet a billion times fainter beside it is one of the hardest problems in observational astronomy. NASA's Roman Space Telescope, set to launch no later than May 2027, carries a coronagraph built to prove this is even possible from space. It's a technology demonstration, a stepping stone, not the final answer. The real target is what comes after it. That's the Habitable Worlds Observatory, a telescope designed from the ground up to hunt for biosignatures in the atmospheres of nearby rocky planets. Proxima b, very likely among them. Some of these instruments were closer to launch than most people realized. Here's the awkward math nobody likes to say out loud. The Habitable Worlds Observatory could be collecting light from Proxima b's atmosphere by the late 2030s or 2040s, hunting for oxygen, methane, water vapor, the chemical fingerprints of life. A probe leaving Earth around the same time, even one riding the fastest propulsion concepts on the table, wouldn't arrive for centuries. So the telescope answers the question first. Not maybe, not probably, first, by a margin of hundreds of years. Any spacecraft launched today would spend its entire flight carrying instruments to reconfirm something astronomers already knew before it left the launch pad. That's not a flaw in the plan. It's just what happens when a beam of light moves at, well, the speed of light, and a spacecraft doesn't. That timing mismatch forced a harder question: why send anything at all? Every serious proposal for interstellar travel eventually runs into that question, and the answers split people fast. Some scientists argue it's about curiosity in its purest form, actually touching another star system instead of just reading its spectrum from 4.2 light-years away. Data is one thing, ground truth is another. Others push back hard on the numbers. A probe the size of a smartphone, accelerated to a fraction of light speed, still faces a flight of decades and a real chance of being shredded by a single grain of interstellar dust along the way. Spend billions, get silence. And then there's the survival argument, colder and less romantic, about spreading humanity's eggs out of one basket. Nobody at these conferences walks away agreeing. One argument in particular kept resurfacing in every serious proposal, and it had nothing to do with curiosity. Earth has been hit before. 66 million years ago, a 10 kilometers rock ended the reign of the dinosaurs in a matter of months. Yellowstone's supervolcano has erupted 3 times in the last 2.1 million years, each time burying a third of the continent in ash. Neither event needs an asteroid to repeat. Gamma-ray bursts, solar superflares, even a nearby supernova could, in principle, sterilize a hemisphere or worse. None of these are science fiction. They're entries in the geologic record, just spaced out over timescales too long for any one person to feel afraid of. That's the core of the backup planet argument. A second, independently thriving human settlement is the only real insurance against a single bad day on Earth. But insurance only works if you can actually get somewhere in time, and that clock was ticking against the mission planners. One answer was to give up on speed altogether. Instead of racing a beam of light, you build a ship that never stops, and you let time do the work instead of engines. Launch it at a fraction of light speed, seal a few hundred people inside, and let their grandchildren finish the trip. A voyage to Proxima Centauri at 1% of light speed would take over 400 years. That's not one cruise mission, it's roughly 15 to 20 generations, born, raised, and buried inside a metal hull, none of them ever seeing the star they're chasing until long after the people who said yes to the mission are gone. Engineers actually like this idea, because slow is easier than fast. You don't need exotic fuel or antimatter, just a big ship, a good life support loop, and patience measured in centuries. Living and dying aboard a ship you'd never see land was a harder problem than propulsion. Start with the gene pool. A few hundred colonists sounds like plenty until you run the math on inbreeding over 20 generations. Most population geneticists put the minimum viable crew somewhere between 10,000 and 40,000 people, just to keep genetic diversity from collapsing before the ship arrives. Then there's the social math. You're asking a closed population to maintain discipline, cooperation, and purpose for 4 centuries straight, with no fresh input from outside and no way to leave. Historians who study isolated colonies point out that even small, well-supplied groups fracture under decades of confinement, let alone hundreds of years. And every person born on that ship inherits a mission they never agreed to. Their great-great-grandparents chose the stars. They just get the hallway. No one has solved that problem yet, not the biology, not the sociology, not the ethics of it. Some scientists thought there was a way to skip this problem entirely, by skipping the passengers. If the crew can't survive being awake for centuries, what if they just weren't awake? NASA actually funded a real study on this. In 2013, SpaceWorks Enterprises received a NASA Innovative Advanced Concepts grant to study torpor, a deep, hypothermic slowdown of the human body for multi-month Mars missions. This isn't cryogenic freezing from the movies. Torpor lowers core body temperature by just a few degrees, slows metabolism, and cuts the food, water, and habitat volume a crew would need by roughly a third. Doctors already induce a milder version of this in trauma patients and cardiac arrest survivors to protect the brain during emergencies. The SpaceWorks concept imagined rotating crew through torpor in shifts, stretching a 6-month Mars trip's resource needs dramatically. Scaling that to a centuries-long interstellar voyage is a different order of problem entirely, and nobody funding this research claims otherwise. The real research was further along than most people assumed, and also far short of what fiction promised. Every fall, an Arctic ground squirrel does something no other mammal on record can survive. It burrows more than a meter under the tundra, curls up, and lets its core temperature fall to almost -3 degrees Celsius, below the freezing point of water. Its blood should turn to ice. It doesn't. Through a trick called supercooling, the squirrel's body fluids stay liquid even past the point where ice should form. Its heart slows to a crawl, its brain activity drops to almost nothing, and it holds that state for up to 3 weeks at a stretch. Then, every so often, it shivers itself back up to a normal 37 degrees Celsius for about a day before dropping again. That cycle repeats for 7 or 8 months straight, all winter, without the animal eating a single bite. Biologists studying it aren't just curious about squirrels. Researchers had already tested a version of this idea on people, not just animals. Doctors have been quietly practicing a form of human torpor for years, just not by choice and not for very long. It's called therapeutic hypothermia. When someone's brain is starved of oxygen after a cardiac arrest or a severe head injury, cooling their body down to around 33 degrees Celsius slows their metabolism enough to buy damaged cells time before they die. There's a far more extreme version too, tested on trauma patients bleeding out on the table with no pulse. In emergency preservation and resuscitation trials, surgeons drain a patient's blood and replace it with ice-cold saline, dropping body temperature to roughly 10 to 15 degrees Celsius. That patient is, by clinical measures, dead. No heartbeat, no brain activity. Surgeons then get a window, sometimes up to 2 or 3 hours, to physically repair injuries that would otherwise be unsurvivable before warming the patient back up and restarting the heart. It's the closest thing medicine has ever done to science fiction cryosleep. But hours of induced torpor was one thing. Surviving years of it was an entirely different frontier. Here's the gap nobody in the field glosses over. The best human torpor trials on record last hours, occasionally pushing toward a couple of days under deep sedation and cooling. An interstellar voyage, even to the nearest plausible target, would require that state to hold for years, maybe decades. That's not a matter of turning a dial further. Extended cooling brings its own damage, blood clotting problems, tissue injury, immune collapse, muscle and bone loss that no amount of monitoring fully solves yet. Even the Arctic ground squirrel has to wake up every few weeks or it dies, and it's had millions of years to perfect the process. Humans have had a few decades of trauma medicine aimed at buying hours, not building a hibernation system built to run unattended for a lifetime. Nobody serious is promising that gap closes soon. While biology struggled to catch up, an entirely different kind of traveler was already being seriously discussed. So skip the body entirely. That was the pitch some researchers floated. Scan a brain, map every connection, and send the pattern instead of the person. No food, no water, no radiation shielding thick enough to stop a heartbeat. Just data, moving at the speed of a laser pulse. The math was seductive. A signal beamed to a waiting receiver at the destination could cross light years without a ship at all, arriving in the time it took light to get there. No centuries of coasting required. Once you had hardware on the other end, you could print a body, or skip the body and run the mind in a machine. A few physicists and AI researchers took the idea seriously enough to write papers about it. not just to speculate around a campfire. It solved the food problem, the radiation problem, and the boredom problem in one move. Not everyone agreed that a copy of a mind counted as actually going anywhere. Here's the snag. If you scan a brain down to its last synapse and run that pattern on a computer light years away, you've built something that thinks it's you, remembers being you, and would swear under oath that it is you. But the original brain, the one still sitting in the scanner, never went anywhere. Philosophers have a version of this that predates computers by centuries. A ship gets rebuilt plank by plank until nothing original remains, and nobody can agree if it's the same ship. Swap plank for neuron, and the argument doesn't get any easier to settle. Some argue continuity is the whole game, that consciousness is a process, not a substance, so a faithful copy really is you, just running on different hardware. Others say you'd die in that scanner every time, and something new, wearing your memories like a costume, would wake up elsewhere. Nobody has found an experiment that proves either side right, and that's still true today. While philosophers argued over minds, engineers were quietly building something that needed no mind at all. A robot doesn't need to eat, it doesn't need air, doesn't need gravity, doesn't panic in a sealed metal box for 400 years. Strip the mission down to instruments, a power source, and a computer, and you've deleted the entire life support problem in one stroke. It doesn't age the way flesh does either. Swap a failing part, patch the software, and in principle the same probe keeps functioning for centuries, limited by materials and power rather than a biological clock. NASA's own Voyager probes, built in the 1970s, are still returning data from interstellar space, decades past their planned lifespan. And a machine sidesteps every ethical tangle a crude mission drags along. No one has to consent to being born on a ship they can never leave. No one has to die en route so the mission continues. No committee has to weigh a human life against a research objective. Send an intelligent probe instead, and the hardest calculus in the whole endeavor simply disappears. Arriving was only step one. What happened after arrival raised its own strange problem. Proxima Centauri sits about 4.24 light-years away, which sounds simple until you think about what that means for a conversation. A probe arriving there can't just call home and get an answer. Every signal it sends has to cross that same distance again, at the same speed, no shortcuts. So the moment the probe reports success, that message takes over 4 years just to reach Earth. Not round trip, one way. Whoever's listening back home has to wait more than 4 years to even know the thing survived the journey. And that's assuming the signal is strong enough to detect at all, stretched thin across trillions of miles of empty space. 4 years of silence was nothing compared to what came next in the numbers. Here's the strange part about that wait. When the signal finally arrives, it isn't telling you what's happening now. It's telling you what happened 4 years ago, a snapshot already out of date the instant it left the transmitter. The probe could have gone silent, drifted off course, or found something extraordinary, and Earth would have no idea for years. Distance doesn't just delay information, it turns every report into a message from history. Stretch that same problem across a mission to a star dozens or hundreds of light-years out, and the lag stops being inconvenient and starts being generational. The people who launched the mission might not be the ones who ever hear back from it. That raises a quieter problem than physics ever could. Who's still around to answer when the signal finally comes in? Space agencies get restructured. Funding gets cut. Entire countries change names within a single human lifetime. A mission plan to report back in 80 or 200 years needs more than good engineering. It needs an institution willing to promise something to people who haven't been born yet, and trust that whoever inherits the project actually keeps listening. No government contract or budget cycle was built with that kind of patience in mind. History already had an example of a message built to outlast its makers. In 1977, NASA launched 2 probes with no expectation they'd matter this long. Voyager 1 and Voyager 2 were built for a 5-year tour past Jupiter and Saturn. Nobody designing them thought in terms of centuries, but they bolted on a message anyway, just in case. Each spacecraft carries a gold-plated copper record, grooves cut with 115 images, greetings in 55 languages, whale songs, thunder, a baby's cry, and 90 minutes of music from Bach to Chuck Berry. Carl Sagan led the team that assembled it, knowing full well it might drift for 1 billion years before anything found it, if anything ever did. The probes finished their planetary flybys and kept going, past the point anyone was tracking closely, out past the edge of the solar wind itself. Decades later, one of those probes was still out there, still talking, in a way nobody expected. Voyager 1 is now about 25 billion kilometers from Earth, moving at 17 kilometers a second, so far out that a radio signal takes almost 24 hours to reach it one way. Voyager 2 trails behind at roughly 21 billion kilometers. Both are still in interstellar space, still returning data, still running on the heat of decaying plutonium. That power is fading by about 4 watts a year, and engineers have spent 2 decades shutting things off to compensate. Heaters, cameras back in 1990, one science instrument on each probe just this year. In 2026, JPL pulled off something they nicknamed the Big Bang, rewiring power on Voyager 2 mid-mission to squeeze out at least 1 more year, with a similar fix now being attempted on Voyager 1. These are machines nearly 50 years old, running code from the disco era, managed by a handful of engineers who've learned a spacecraft that predates the internet by inches at a time. Voyager proved a probe could last decades, but a relativistic mission demanded something built for centuries. A ship traveling toward another star isn't gone for 5 years or 50. Depending on how close it gets to light speed, it could be in transit for hundreds of years before anyone back home even knows if it worked. That timescale breaks almost everything engineers know about spacecraft reliability. Electronics degrade even sitting still. Solder joints crack from thermal cycling, capacitors dry out, memory chips lose their charge over years, not centuries. Deep space adds cosmic radiation that slowly scrambles circuits no shielding fully stops, and metals grow brittle in cold that never lets up. Voyager's instruments were simple enough and close enough to home that engineers could patch problems with a software update. A starship centuries into a journey of light years would get no such rescue. One proposed fix came from an unlikely source: the way ancient monuments were built to last. Aerospace engineers call it redundancy, but it's closer to a doctrine. Every critical system on a deep space probe gets a backup, and that backup often gets a backup of its own. Triple redundant flight computers vote on the correct answer, so if radiation flips a bit in one, the other 2 overrule it. Voyager carries 2 of nearly everything: 2 radio transmitters, 2 computer command systems, backup gyroscopes waiting in reserve. Mission planners run failure trees years before launch, mapping every part that could break and asking what happens next. If a heater fails, does a fuel line freeze? If a fuel line freezes, does the whole mission die with it? For a mission measured in decades, this kind of layered backup buys real time. For a voyage measured in centuries, the math gets harder. Even with every backup imaginable, there was one failure mode no redundancy could fix. Radiation doesn't strike a spacecraft's electronics like a single dramatic hit. It accumulates, particle by particle, over years of exposure. Cosmic rays and solar particles slam into silicon at the atomic level, knocking electrons loose and slowly corrupting the transistors that make a computer chip function. Engineers call the buildup total ionizing dose, and every chip has a threshold before its logic starts failing in ways no software patch can fix. Doubling a chip up won't save it if the same radiation degrades both copies at the same rate. Memory cells forget. Sensors drift out of calibration. Solar panels lose efficiency year after year as their crystal structure quietly breaks down. None of this happens fast enough to notice in a 5-year mission. Stretch that same exposure across 100 years, or 1,000, and it becomes a hard ceiling on how long any electronic brain can survive. One family of materials was already showing promise against exactly this kind of decay. Metal halide perovskites, a class of crystal first identified in the 1830s, turned out to do something conventional silicon can't: recover. Researchers testing them as radiation-damaged solar cells found the material's structure reforming itself after exposure, undoing damage that would be permanent in ordinary semiconductors. NASA's own labs have been chasing a parallel path with radiation-tolerant computers that check their own health in real time, built from redundant, reconfigurable processors that can rewire around a damaged component instead of just outvoting it. One version has already been slated to fly to the lunar surface, riding through the Van Allen belts as a real-world stress test. Chipmakers building dedicated rad-hard processors for deep space are promising several times the computing power of anything currently flying, at a fraction of the power draw. None of this mattered, though, unless the probe survived the trip itself in one piece. Surviving the trip was only half the problem. Getting a probe up to a fraction of light speed takes a staggering amount of energy, but stopping again takes almost exactly as much. Physics doesn't offer a discount on the way down. A craft moving at 20% the speed of light carries kinetic energy that has to go somewhere. You can't just cut the engines and coast into orbit around a star system. Without a way to shed that speed, the probe would blow through its target in a fraction of a second. Cameras barely able to focus before the whole system was behind it. That single fact quietly doubled the propulsion problem engineers thought they'd already solved. Every gram of fuel spent accelerating now needed a matching answer for deceleration, and no one had carried enough fuel for both. Slowing down turned out to need its own separate breakthrough, one nobody had solved yet. One idea skips fuel altogether: a magnetic sail. Essentially, a giant loop of superconducting wire could generate a magnetic field wide enough to push against the thin stream of charged particles drifting through interstellar space. Ride that drag long enough, and a starship could theoretically break without burning a single extra ounce of propellant. Other proposals lean on the same idea in cruder form: unfurl a huge physical sail and let collisions with stray hydrogen atoms do the work, shedding velocity over years instead of igniting an engine that can't be resupplied. On paper, the math checks out. At interstellar scale, nobody has built one, and the particle densities out there are so low that some estimates put the braking distance in the trillions of kilometers. A sail wide enough to matter would also need to survive micrometeorite impacts for decades, unfolding perfectly the one time it gets to try. Even the most promising braking system carried a hidden cost that engineers hadn't fully reckoned with. Faced with an arrival problem this stubborn, a lot of serious mission concepts just gave up on stopping. Instead of orbit, they aim for a flyby, screaming past the target system at full relativistic speed and gathering whatever data the instruments can grab in the window available. For a probe moving at a meaningful fraction of light speed, that window isn't hours, it's seconds. Cameras and sensors have to be pre-programmed years in advance, executing a fixed sequence with no chance to react, no chance to slow down for a better look, no second pass. It's a strange trade: decades, maybe centuries, of travel time spent on a target that flashes by almost too fast to register. Every angle, every measurement has to be decided long before launch, gambled on a single irreversible pass. Seconds of data, after decades of travel, forced planners to ask if it was worth it at all. But mission scientists push back hard against that math. A flyby isn't measured in hours of contact, it's measured in what those hours reveal. You can spend 10 years traveling and 1 minute observing and still come home with data that reshapes an entire field. The instruments don't need to linger. A camera resolving surface features for the first time, a spectrometer sampling an atmosphere no one has ever touched, a magnetometer catching a field line that theory only guessed at. Each of those readings lands in seconds and gets studied for decades. Skeptics call it a gamble. Scientists call it the only kind of exploration physics currently allows. One real mission already proved that a fleeting pass could rewrite an entire textbook. In July 2015, NASA's New Horizons spacecraft swept past Pluto at over 49,000 kilometers per hour, its closest approach lasting less than a day. Before that flyby, Pluto was a blur, a handful of pixels even to the Hubble Space Telescope. Nobody knew what its surface actually looked like. Then the images came back. Mountains of water ice standing 3,500 meters tall, a heart-shaped plain of nitrogen ice, still geologically active, still shifting, a hazy, layered atmosphere, far more complex than any model had predicted. That single pass produced more Pluto science than the previous 85 years combined, and researchers are still publishing papers from that dataset today. That mission had taken nearly a decade just to arrive, and Proxima was orders of magnitude farther. New Horizons launched in 2006 and reached Pluto in 2015, covering roughly 5 billion kilometers, a journey that stayed entirely inside our solar system. Pluto orbits at about 40 AU from the Sun. Proxima Centauri sits at 268,000 AU. Scale that Pluto trip up to Proxima's distance, and the same spacecraft, at the same speed, would need something like 78,000 years to arrive. Not a mission a single agency plans for. Not a mission a single generation lives to see. Every propulsion system humanity has ever built, chemical rockets, ion drives, even nuclear thermal engines, tops out at speeds that make that number worse, not better. Every technology discussed so far still fell short of what this distance actually demanded. There was one exception, one idea that didn't just push the ceiling higher, it broke the ceiling entirely. Antimatter. Every rocket humanity has built burns fuel and throws most of its energy away as heat and waste. Antimatter doesn't burn. When it meets ordinary matter, all of it, every last bit of mass, converts directly into energy. No leftover ash, no wasted potential. A single kilogram carries roughly 10 billion times the punch of the same mass in TNT. In theory, a spoonful could outperform the fuel tanks of 24 space shuttles combined. That's the kind of number that makes an interstellar crossing feel almost reasonable again if you can get your hands on the fuel. And as it turns out, humans have been making antimatter, on purpose, in a lab, for decades. One facility had just pushed antimatter production further than ever before. That facility sits underground at CERN, on the border of France and Switzerland, inside something called the Antimatter Factory. Since the 1990s, physicists there have been manufacturing anti-hydrogen atom by atom, then trapping them in magnetic fields so they never touch normal matter and vanish. In November 2025, a team at the AD-ELENA program hit a real milestone. Using laser-cooled beryllium ions, they cooled positrons below 10 Kelvin, colder than ever managed before, and trapped 15,000 anti-hydrogen atoms in under 7 hours. Previous methods needed a full day just to catch 2,000. That same month, the BASE experiment did something no one had tried. They loaded trapped antiprotons onto a specially shielded truck and drove them across the CERN campus to another lab, the first time antimatter had ever been transported anywhere. Real progress, genuinely historic. And still, after 30 years of refining this process, CERN's entire antimatter factory produces about 1/1,000,000th of a gram of antimatter in a year. The gap between what CERN could make and what a starship would need was almost too large to say out loud. Half a gram of antimatter, meeting half a gram of ordinary matter, releases enough energy to level a city. At CERN's current output, reaching that half gram would take roughly 500 million years of continuous production. That's just to arm a bomb. A starship needs to sustain thrust for years, not flash annihilate once. Robert Frisbee's NASA-backed study on antimatter rockets calculated that a two-stage ship reaching half the speed of light would burn through over 800,000 metric tons of antimatter fuel for the trip. Run CERN's production line at full tilt every hour of every year, chasing that number, and you're not looking at centuries. You're looking at timescales that make the age of the universe seem like a rounding error, trillions of years deep, for fuel that would still detonate the instant containment failed. Even the physicists who'd spent their careers building the trapping equipment described the propulsion dream as, in their own words, a waste of time at current rates. But not everyone accepted that the math was final. A handful of physicists believed there was still a way to shortcut that number. If you couldn't afford antimatter at $62.05 trillion a gram, one option was to stop building it and start looking for it instead. A few engineers, including James Bickford at Draper Laboratory, ran the numbers on a wilder idea. What if a planet's own magnetic field was already doing the manufacturing for you, for free, and had been doing it for billions of years? Cosmic rays slamming into a planet's upper atmosphere don't just make heat and light. Sometimes that collision splits energy into a particle and its antimatter twin, a process physicists call pair production. Most of it destroys itself instantly. But a magnetic field strong enough could, in theory, catch some of that antimatter before it does. Earth has exactly that kind of magnetic field. So does Jupiter and Saturn, only bigger. The proposal was to build a magnetic scoop, park it in orbit, and let the planet hand over antimatter it was already making. That idea alone was strange enough to sound like science fiction, and yet it had already been observed. In 2006, the Italian-led Pamela satellite launched to study cosmic rays, and it flew straight through a region called the South Atlantic anomaly, where Earth's inner Van Allen belt sags closest to the surface. Over roughly 2.5 years, its detectors caught something nobody expected to see in such numbers: 28 antiprotons orbiting Earth, trapped. That doesn't sound like much, and it isn't. But the antiproton annihilation events researchers picked up were happening about 1,000 times more often than a universe with no trapped antimatter would produce. The prediction had been made decades earlier. This was the first direct confirmation that it was true. Bickford had already calculated that a magnetic scoop of superconducting coils floated in equatorial orbit could collect antiprotons at a rate of around 25 nanograms a day, and do it at a cost roughly 100,000 times cheaper per gram than a particle accelerator on the ground. The amount detected so far was tiny, but it hinted at something the whole video had been circling since the beginning. Because none of this was ever really separate: the propulsion problem, the energy budget, the years that stretch into centuries for the people left behind, the belts of antimatter quietly renewing themselves around planets that had never asked to be fuel depots. Each piece had been sitting in a different part of the story, waiting. A ship that could reach even a meaningful fraction of light speed needed an energy source almost nothing on Earth could supply, except the one substance whose entire existence seemed built around defying that same limit. And the limit itself wasn't just a speed. It was a relationship between energy, mass, and time that showed up again in every dead end this video had already walked through. Harvesting, containment, deceleration, the long silence of a multi-generation flight. They weren't four separate problems anymore. They were starting to look like the same problem, viewed from four different angles. Every dead end, every workaround, had been quietly building toward one answer nobody had said out loud yet. So here's the question again, the one sitting underneath everything since the opening frame. If nothing with mass can reach light speed, and the gap between stars is measured in trillions of miles, how does anyone actually get there in a single human lifetime? Not a faster engine, not a clever shortcut through the rules. The real question is whether there's a loophole physics itself left open, something that doesn't break the limit but slips around it. Every antimatter dead end, every fuel problem, every impossible price tag has been circling that same opening. And the answer, it turns out, was never about going faster at all. If building antimatter on Earth takes 1 trillion years at CERN's current pace, maybe the trick is not to build it. Maybe it's already out there, waiting. Earth's own radiation belts trap tiny amounts of antiprotons, flung into orbit by cosmic rays slamming into the upper atmosphere. Physicists have sketched satellite collectors for decades, magnetic funnels shaped to catch charged antiparticles and hold them without letting them touch normal matter and vanish. On paper, it's elegant. No accelerator, no decades of collisions, just a net cast into a belt of particles the planet makes for free. One tiny mission already tried to catch this stuff, and what it found changed the math. That mission was real. Pamela, a satellite-borne detector launched in 2006, spent years sweeping through Earth's magnetosphere, logging particles. And it confirmed what theorists had guessed. Antiprotons really do collect in a band around the planet, concentrated near the South Atlantic anomaly. A follow-up analysis using the AMS-02 detector aboard the space station estimated the total supply trapped there at any moment. It came out to about a nanogram spread across the entire belt. A nanogram, billionths of a gram, drifting in a ring around the whole Earth, the accumulated harvest of a natural process running for millions of years. The number needed to fuel a real voyage makes that satellite's haul look like a rounding error. Here's the wall every workaround eventually hits. A milligram of antimatter, fully converted, releases about 43 terajoules. That sounds massive until you run the numbers for an actual starship, one big enough to carry people, shielding, and decades of supplies. To reach even 10% of light speed and slow back down again, mission designs land in the range of tons of antimatter, not grams, not milligrams, tons. Every particle accelerator on Earth, running flat out since the 1990s, has made a few billionths of a gram total. Warp metrics need exotic energy nobody's found. Wormholes need exotic matter nobody's built. Solar sails are too slow. Generation ships trade speed for centuries of human cost. Swap the method and the wall doesn't move. Every path this story has followed keeps leading back to one uncomfortable idea. So go back to where this started. A ship, alone, crew strapped in, the reactor core reading numbers no engineer on Earth had ever seen live. You watched that moment without knowing what it cost to get there. Now you know what's underneath it. You know the antimatter had to come from somewhere impossible, harvested by the milligram over years, stored in a trap that fails if the power blinks for a fraction of a second. You know the fuel alone could have been a national budget. You know the math said tons, and somehow this ship was flying anyway. That gap between what physics allows and what the mission needed is exactly where the tension in that opening scene was hiding the whole time. What actually happened aboard that ship is about to make sense. The ship never broke the speed of light. Nothing did, nothing can. What the crew felt in that opening moment was their own clock slowing relative to Earth's. Time dilation doing exactly what relativity predicts as they pushed past 90% of light speed. The reactor spike you saw wasn't triumph. It was the antimatter core burning through its entire reserve in one sustained, controlled annihilation, converting mass to thrust at the only efficiency high enough to make the math close at all. That's the real answer. Not a loophole around the limit, but a civilization that learned to spend a substance so rare it's measured in atoms, just to nudge a ship close enough to light speed that the universe itself bent time around it. No warp bubble, no shortcut, just mass, converted at 100% efficiency, buying a few more minutes of light speed illusion before the fuel ran out. The speed of light isn't a wall built to keep us out. It's the frame that holds everything else in place. Without it, effect could precede cause. A signal could arrive before it was sent. The past could rewrite itself midstream. Relativity doesn't forbid faster-than-light travel because the universe is stingy. It forbids it because causality, the logic that lets one moment follow another in a sequence you can reason about, depends on that limit. Break it, and you don't just travel backward in time. You shatter the order that makes time, memory, and consequence possible at all. Every loophole we've examined, warp drives, wormholes, tachyons, collapses under the same weight. They either require impossible energy, invoke particles that can't interact with matter, or open paradoxes that erase their own setup. The barrier holds because the alternative is a universe where logic itself becomes optional. None of this changes why humans keep trying anyway. We mapped the Alcubierre metric, knowing it demands negative energy we've never seen. We calculated antimatter fuel loads that would take 130,000 years to gather naturally, then started sketching magnetic scoops to harvest trapped positrons from Earth's radiation belts. We built particle colliders that produced 10 nanograms a year and called it progress. The gap between what we want and what physics allows isn't evidence of failure. It's the gap every technology crosses, one implausible step at a time. Heavier than air flight was thermodynamically possible but materially absurd until 1903. Splitting the atom was theoretically predicted decades before anyone held enough purified uranium to try. The researchers publishing antimatter storage papers today, the teams modeling magnetic nozzles for photon rockets, the students running relativistic simulations on university clusters, they're not chasing a fantasy, they're charting the boundary, mapping what's forbidden, what's merely impossible right now, and what's expensive but real. One small, real detail about the people chasing this dream says more than any equation could. You started this video watching a ship that couldn't break light speed try anyway, burning antimatter just to stretch time until the stars slid close enough to touch. You learned why the limit exists, what it would cost to approach it, and why every shortcut we've imagined folds back into the same wall. The cold open resolved itself not with a miracle, but with physics doing exactly what it promised. If this is the kind of thing you want more of, real physics, no hype, just the math and the consequences, hit subscribe. More videos on propulsion, relativity, and the actual constraints on interstellar travel are already live. In 1977, Voyager 1 left Earth carrying a golden record, a map, and a handful of human voices pressed into metal. It's now 15 million miles out, moving at 38,000 miles per hour, and it'll take 40,000 years to drift past the next star. The engineers who launched it knew they'd never see it arrive. They built it anyway, panel by panel, knowing the only message it would ever deliver is that we tried. Go back to that opera detector in 2011 for a second, because the cable was only half the story. The fiber connector was screwed in just slightly loose, enough to add about 73 nanoseconds of delay to the timing signal. That's almost exactly the size of the anomaly they'd found. Once technicians tightened it, the faster-than-light result vanished completely, and neutrinos went back to obeying the speed limit. The Alcubierre warp metric, when Miguel Alcubierre published it in 1994, needed a mass roughly equal to Jupiter, converted entirely into negative energy. Later refinements by other physicists shrank that number, but even the most optimistic versions still need more exotic mass energy than humanity has ever produced or detected in a lab. That's the gap between a valid solution to Einstein's equations and something you could actually build. The Casimir effect, the real experiment behind theoretical negative energy, was first measured precisely in 1997 by Steve Lamoureux at Los Alamos. Two uncharged metal plates, placed a few hundred nanometers apart in a vacuum, get pushed together by a measurable force. It's proof that negative energy density isn't science fiction. The problem is the effect is almost immeasurably small, nowhere near the scale a warp bubble would need. Breakthrough Starshot's math is worth sitting with. The plan calls for a sail about 4 meters across, weighing just a few grams, pushed by a ground-based laser array delivering 100 gigawatts. At that power, the sail would reach roughly 20% the speed of light in just a few minutes of acceleration, then coast the rest of the 4.24 light-years to Proxima Centauri. The laser array alone, if it were ever built at full scale, would cost more than the Apollo program adjusted for inflation. Antimatter production at CERN gives you a sense of the real bottleneck. Their antiproton decelerator makes antiprotons, but at a rate so slow that producing just 1 gram would take longer than the current age of the universe at present output. Scientists have calculated it's the most expensive substance ever made, running past $60 trillion per gram by some estimates. Storing it is its own problem too, since any contact with normal matter triggers annihilation, so magnetic traps have to hold it suspended in a vacuum, untouched. Voyager 1's plutonium power source loses about 4 watts of output every year. By the early 2030s, mission engineers expect they'll have to start shutting down instruments one by one just to keep the transmitter alive. It's not a dramatic failure. It's a slow, planned fade, subsystem by subsystem, until one day there's nothing left to power the radio at all. The limit stands, the light still travels, and somewhere in the gap between them, we keep building,